Now, yeah. Okay, so welcome to the morning session of this plenary session. Today we start with Wojciech Domic from the Warsaw University of Technology. He's going to talk about asymptotic lines and curvature lines defined by the Gauss map of surfaces in R4. Thank you, Wojciech.
Thank you very much. I would like to thank the committees of this conference, of this nice conference, for invitation and giving me opportunity to speak here on this special workshop dedicated to Cidinha. I must confess that I do not remember when I first met Cidinha. Probably it was in the Banach Center. I remember her second visit when she stayed longer. At that time, she presented me Jacob de Bandolin. She was extraordinary person, a recording of Jacob de Bandolin, short music. I didn't know this music. She was very interested in music. And she was extraordinary person. And, you know, when you are young, many young people coming to mathematics because of competition, yes? But Cidinha changed this word, competition, to collaboration. And this was the strength of the Brazilian group. I'm not sure if the data are correct. I checked it yesterday in the MathSkyNet, and she has 76 collaborators from many countries. For many countries. I have the honor to write 2 papers together with her. Yeah, so maybe mathematics is a kind of competition, yes. Maybe it's like football, but if it is a football, it's a team competition. So we are all mathematicians in one team. And this was the spirit of Cidinha, is to collaborate together because we want to understand mathematics just. Yes. When I think about her, I think about joy of mathematics. I believe that she never stops to do mathematics, even now. Yeah, she joy life, she joy mathematics, she joy mathematics. Okay, so I will talk about my joint collaboration with Yvonne Hernandez Martinez and Sanchez Bringas from Mexico. I will talk about asymptotic line and curvature lines defined by the Gauss map of surface. This is continuation of the talk that I have 2 years, I think, or 3 years ago here. And from this conference, I get new ideas how to prolong this. Maybe this is switch off, no? Oh, no, this is okay. How to prolong my work. Okay, so how to go? Okay, so I will define what is the Gauss map. So we have a smooth oriented surface in R4 and immersed, and the Gauss map just assigned to each point of its oriented surface just its oriented tangent plane. Yes, so each map for G of P of a point on M gives the tangent space. It's a subspace of Rn. Okay, so we have 2-dimensional oriented subspaces in R4. Okay, so we are in the oriented Grassmannian of 2-dimensional subspaces. Okay, it has a special structure. This structure was studied by many people, by Chern, by Spanier. We can use the Plicker coordinates on this space. So if we just fixed positive orthonormal basis of R4. It is E1, E2, E3, E4, okay? And if we take a V is a 2-dimensional plane, yes, oriented, then we can take a positive orthonormal basis, V1, V2, and take just this wedge product, V1, V2, and we can decompose it because the bivectors E1, E2, E2, E3, E3, E1, and so on, there are 6 of them, yes, they form a basis, yes, and the image of this of this map, because you see we start from the two-dimensional spaces in the Grassmannian are characterized by these two equations. The first equation is because this is simple bivector. Yes, simple one. So if you take it with itself, it must be 0, simple or decomposable. And the second one, because we have this basis is orthonormal, so we can define just the prolongation of the scalar product to bivectors by the following formula. So if you have a bivectors V1, V2, and W1, wage W2, so you define the scalar product in the following way. You take just determinant of V1, W1, V1, W2, V2, W1, and V2, W2. Okay. So you can prolong it, and then this decomposable vector, which is from orthonormal basis constructed, satisfies this equation. Yes, the coefficient. Yes, because something happened. I pressed something. No, I don't know what's happened. Something disappeared. I don't know why. Maybe I pressed something. What? Ah, okay. Okay. Oh, thank you very much. Okay. Okay. But we could take another basis. This is also orthonormal basis in the space of bivectors. This is adapted to the Hodge splitting. X1, X2, X3 in the following way. This is orthonormal basis, and Y1, Y2, Y3. Yes? These are dual with the Hodge splitting. This is anti-dual, but doesn't matter. Okay, so anyhow, if you take this basis and you write your bivector, the conditions for the bivector and this basis, yes, then you got these equations. You see? You got these equations. So the image of this Grassmannian in these bivectors in R4 is just two spheres. And since we have the scalar product, we can even say what exactly are these spheres. This is a spheres of the radius 1 over square root of 2. Okay, so we denote by these two spheres by S1, the first one, and S2 by the second. Okay, okay, and then we will have two components of the Gauss map, yes, because we can use just projection, compose our Gauss map with the projection from this product of two spheres to SI, okay? And we denote by GI the first component of the Gauss map and the second component, okay? And these two spherical maps encode tangent planes through the self-dual and anti-self-dual parts of this the space of these two bivectors. Why we did so? No, first of all, if you have a map, it's good to know to what space it's going. Yes, and the second of all, because if you have a Gauss map of a surface in R4, generically it has no singularities. Generically, it's immersion. It was proved by Little many years ago. Okay, but these maps, these components can have singularities, and generically they have singularities. These singularities I will describe. Yes, because they are maps from the surface which is of dimension 2, to the sphere, which is also two-dimensional. Okay. Okay, so now I will describe this map using this. Now, maybe it is a little bit misleading, but from now on, this E1, E2, E3, E4 is a not fixed basis of the linear space R4, but it's a local Darboux frame, yes, on U, the subset of M, of our surface. So what it means? So it is positive, orthonormal frame at each point, yes, and such that the first two vectors are span the tangent spaces, and this is positive orthonormal basis of TPM, yes? Okay, then the Gauss map is just give E1, E2 at each point, yes? Okay, and this components G1 is just, if in the previous notation, in just 1 over square root of x1, and G2 is 1 over square root of y1. Yes, so this is the advantage of this if you use this basis. Yes, okay. Of course, x1, x2 are now also orthonormal frame at each point. You know, this is maybe a little bit misleading because first they were just in a point, but now they are at each point of view. Okay, okay, and now we will use the Cartan method of moving frame. So I recall it because we will use it a lot. Okay, so we have this immersion. I denoted it by F. From M to R4, this is our immersion of our surface into R4. Yes, then we can take dF, and it is decomposed into θ1 E1 plus θ2 E2. Yes, because it goes to the tangent space. Yes, okay, and E1, E2 are span the tangent space. θ1 are the dual forms. Yes, so this is exactly the scalar product of dF and EE, yes. We can do it for 1 to 4, yes. And when we define the connection form I defined in this way, if you take the differential of EI, then you get this, that it can be decomposed to the space of E1, E2, E3, E4, and these coefficients are the coefficients of the connection form, yes? And since we are at the points of our surface, E3, E4 are zeros, and since we use the orthonormal basis, we have this antisymmetry, yes, which implies that on diagonal we have 0, and the Gaussian curvature and the normal curvature can be obtained by this equation, yes? This structural equation, in fact, is hidden here. Okay, so d omega 1, 2 is minus Gaussian curvature times θ1, θ2, and d omega 3, 4 is minus normal curvature, θ1, θ2. Okay. Okay, and then we can write how it looks like. No, G1, G2 I already described. So then you can, by easy calculation, you can calculate dG1 and dG2. Okay, and then if you take this describes in some sense the determinant of this map, because if you take this wage product, this is determinant, then you obtain that the determinant of G1 is equal to Gaussian curvature plus normal curvature. And the determinant of the G2 is Gaussian curvature minus normal curvature. In fact, it was proved by Blaschke in 1945 and when discovered by Weiner and Hoffmann-Ossermann that the Jacobian of G1 is 1/2 of the sum of the curvatures, and the Jacobian of G2 is 1/2 of the difference of the curvatures. Yes, the Jacobian we defined using the standard area form on SI and the area form on M. Yeah, then by this equation, which you have previously, yes, this one, you see that you have to multiply this by this, the wage product of This is the batteries one. This one, and then you obtain this result. Okay. Okay, and the singular set of our map is this, yes, for GI, yes. CI is the singular set for GI, yes. So this is the Gaussian curvature plus normal curvature or Gaussian curvature minus normal curvature. Okay, okay, and now the generic properties of GI. GI can have singularities, yes. So for generic immersion, the following hold, that the singular set is smooth, yes, and the kernel line field of our map, GI, yes, this is the kernel, in fact, yes, you see easily from the equation from DG1, DG2, and this kernel is transverse to the singular curve, except a finite many points where it has first order tangency, cusp, on the other are faults. Yes, okay, so this is, and also we have the condition about self-intersections. Yes, if we have self-intersection, they intersect only in faults and the tangent lines are transversal. Okay, so we prove that these properties are generic. For this, we use just the projection of what's the stereographic projection to describe as S1, S2, but it can be also obtained just using this moving frame. Yes, so we prove that this, which satisfies this generic condition 1, 3, this is our cusp and faults, and so, and they are generically stable. Okay, okay, now here I talk about this, and then I didn't know, I think Huang Ho asked me a question that we should describe these singularities with something which is with some contact with some object. I didn't know what is the object, but Lemmy Langevin, after my talk, said me that he knows what is the object, and the object is holomorphic curves. Yes, and in fact, it was even, Remy just pointed me, that it was in the paper of Hoffman-Osserman, that this map GI is constant if and only if there exists orthonormal complex structure J on in 4, which preserve the orientation. I shouldn't say like this. There always exists such orthonormal complex structure which preserve orientation for I and reserve orientation, yes? And we have a holomorphic curve with respect to this orthonormal structure. This orthonormal, not orthonormal, orthogonal structure. What it means? J is orthogonal, so it's constant, yes? It does not change from point to the point. Okay, and this identifies the constant components, and we have to study, I have to speed up, we have to study the contact with these complex curves. Okay, so we defined also G1 elliptic, G1 hyperbolic, G1 parabolic. You think maybe that I make mistake. I did not mistake because there will be minus in front of this. Okay, and then we study the contact of our surface with these holomorphic curves. Yes, if you use just Monge coordinate, the holomorphic structure is the usual standard holomorphic structure on R2. Yes, and then we use the contact, this contact equivalence. Okay, so we prove these results. Yes, so we can describe these singularities of G1 and G2. This is for G1, for G2 is the same, by the contact with the holomorphic curves. This is just a jet of the contact function. But this calculation was very complicated. We use Mathematica for this. So for example, the point 5, the calculation, it's if you print it, the calculation of the Mathematica results, the comments are short, but the results are very, very long. So it was 237 pages. Yeah, so okay, we get it what we wanted, but we were not satisfied with this result because you can never check it by hand. Yes, it was complicated. So we were looking for some other description of these singularities, and this is we find some quadratic form. Okay, so we do it in the case when the mean curvature, I will explain later, the mean curvature vector, which is here, yes, this is H, is the mean curvature vector, does not vanish. For this mean curvature vector, if it's not vanish, you can define the orthogonal to it. Yes, so this is orthogonal and also it has the same norm. And then you can define such a smooth bilinear form. Yes? Okay, I have a lot of time, yes? Because I thought that I have to finish in 10 minutes. Okay, I don't have to speed up. Okay, sorry. Okay, so we have this, H. This is mean curvature vector. We assume that it does not vanish. Okay, then we have the orthogonal to it, defined by this equation. So we have this one, which is orthogonal, and same norm, yes. And when H is not equal to 0, so H and H orthogonal is a positive basis of the normal bundle, yes, because the H belongs to the normal bundle. And this is orthogonal, but I mean orthogonal, yes, of course, it's a one vector, but we take only orthogonal in the normal bundle. Okay, and then we can define bilinear form in this way. So you take dgi on v is a vector, tangent vector, yes, w is also tangent vector, and here you take the wedge product of H orthogonal with W, yes? We use this scalar product because both are in fact bivectors, yes? The image of dgi is a bivector and this is bivector, okay. And it is easy to prove that it is smooth, symmetric, bilinear form, okay. Okay, this is the proof. The proof is easy because if you describe this like this, yes, then you can calculate the coefficient, and here you have the same b. Yeah, you have the same b in front of theta 1, theta 2, and theta 2, theta 1. Yes, the same b. Of course, as you see from the definition, if we have a point where H is vanished, then H orthogonal is also vanished because you can use just this formula and define H orthogonal just taking the coefficient in front of E4 with minus and the coefficient and put it in front of E3 and this coefficient in front of E3 put into E4 without changing the sign, and then you have the orthogonal. So you see, so this has the property that this bilinear form vanish when H vanish. Okay, so it can be easily seen from this coefficient. Okay, so this is the coefficient of this bilinear form, and then we define this quadratic form for GI just taking the corresponding quadratic form. Yes, it has the same coefficient. Yes, it looks like this. Its discriminant, you see here is the -1. Yes, -1/4. Therefore, we elliptic, parabolic, hyperbolic. Parabolic is the same, but hyperbolic and elliptic looks very strange that we use just the difference. Okay, and just the sign of this controls the type of this quadratic form. Okay. Okay, and why this quadratic form is useful? Because we have the following theorem. If you take the second fundamental form of our surface minus the second fundamental form of holomorphic curve with the same tangent plane, yes, for each tangent plane there is such exist, then you can write it, this difference, or -1 to I difference, I is 1 or 2, is just in this way, yes? I think that should be minus I to I plus 1, sorry. This minus 1 to the power I plus 1, because for G1 it should be plus, for G2 it should be minus. Okay. And this holomorphic curve, it's not rather holomorphic curve, but it's first fundamental form, second fundamental form, not first, second, I should say second. Second fundamental form are the time uniquely by this condition, that if you project it to the direction of H orthogonal, then it's agree with this projection, with the projection of our second fundamental form of our surface. At this point, so at each point we have different, yes, holomorphic curve, but this contact with this holomorphic curve describe the singularities, yes? So it's coding in this, yeah. So this is geometric description, what is going on and why we have this particular quadratic form. In fact, we know this, but then I find this formula for this. This formula is very easy somehow. Okay, what is if we have the point when H, the mean curvature vector vanish? Then for this point, if you take any normal vector, then there exists a holomorphic curve such that this satisfied this, yes, a similar formula to this, yes? But in any direction you have it, you can find different holomorphic curve. It's not unique like in this case. In the H is not equal to 0, there is only one such. Okay, up to the second fundamental form. Okay, the proof is not difficult. You have to write how it looks like the second fundamental form. This is the second fundamental form of our surface. Yes, due to symmetry of this, we have this condition, yes? This is obvious condition because we have orthonormal basis. And how it looks like the second fundamental form of the holomorphic curve, it looks like this. So the coefficients have this symmetry. There are only two coefficients because if how it looks like, you just take the just C1 plus I C2 times Z to the power 2, and then you got it. Yes, in fact, yes. So you have only two coefficients, yes. And now if you subtract, yeah, if you subtract, then we choose a special Darboux frame such that we take for the basis of the normal part of our frame just the mean curvature vector divided by its length, and E4 is just the orthogonal to it divided by its length. Okay, and then if you look for the equation that has to be satisfied by the mean for the definition of the mean curvature vector, you have that this condition are satisfied. Okay, so omega 2, 4, E2 is minus omega 1, 4, E1 because our E3 is H divided by the norm, so the other components must vanish. Okay, and then if you put it to this equation, then there is unique solution. You see, this is the only solution which satisfies this, and this is the proof. Very, very easy. Okay. Okay. Okay, and now we can define asymptotic direction for these components, for this quadratic form of the components. So these are the direction in which this, in which this quadratic form vanish. Okay, standard definition. And And this are the direction that this holomorphic curve higher order of contacts, yes, with our surface. And if P is hyperbolic, there are two. And GI asymptotic direction, if P is parabolic, there is only one. No one if you have elliptic. Okay, and now how they looks like, you can describe them, yes? At the points when the mean curvature vector does not vanish, yes, and we have a positive Darboux frame with E3 equals to H divided by the norm of H, when E4 is automatically this one, which we have the orthogonal divided by the length. And if we assume that the curvatures, sum of curvatures at this point are not positive, then we have such form, yes, and then we can define, this is our asymptotic direction. We have two different formulas depending since one of the coefficients has not to vanish. So if one coefficient is not vanish, is this formula, if the other is this formula. Okay, but one of them has to be vanished because this is cannot vanish because we have this Gaussian curvature plus normal curvature is not positive. Okay, okay, and using these forms, we can describe using this form, we can describe the singularities. We get the geometric explanation. Yes. Okay. So if we have a point in which the mean curvature does not vanish, then P is a simple fold of this quadratic form. We use the Dara results, yes, which were extended by Davidov, by Cidinha, by Bruce, and Farid, and so on. And many people work on this, but we use this first results by Dara. Okay, so P is a simple fold of this quadratic form, if and only if P is a fold of GI. P is a saddle of this quadratic form, when P is a negative cusp of GI. Yes, the cusp if you have in oriented space, the cusp are positive and negative, depending on the orientation, preserving or not. And P is a folded node or focus of this quadratic form, when P is a positive cusp of GI. Yes, so this local dynamics of asymptotic lines are the types of the singularity of GI. But there are also some simple, formulas that we can find later for these quadratic forms. So you look, the first quadratic form is just 1/2 of a pullback of the first fundamental form of cis1 plus it's Jacobian because it's a 1/2 of Gaussian curvature plus normal curvature times the first fundamental form of M. And for G2, we have the same formula, only here we have Jacobian of GI, and the sign here is minus. Yes? Okay. So this QGY can be described in this way. Okay, but it's recall maybe some of you some formula. In fact, using this, you can prove this classical formula which relates third fundamental form. At third fundamental form, if you look, it is just the pullback by G, by the Gauss map, of the first fundamental form no, this is not like this. This is this formula. No, this is not, because we have two spheres. Okay, so this is the formula for the third fundamental form. And when this is Gaussian curvature plus first fundamental form of M plus 2, that's mean curvature vector scalar product with the second fundamental form. This is the classical formula for the relation of the third, second, and and first, second, and third fundamental forms. This formula can be obtained from these formulas in such way, because this, if you take Gi star of the first fundamental form of Si, then it is just dgi, dgi. Yes? Okay. And then, if you notice that dg1, dg2, since they are in these orthogonal components, they are orthogonal, then you get this by the simple calculation. You got this formula from these two, just subtracting them, okay? And consequently, the right-hand side is just the difference of this quadratic form for G1 and G2. Yes, because here, look, there is plus sign and here is the minus sign. Yes, so you have to subtract them. From dg1, you have to subtract to dg2. Then here you obtain just Gaussian curvature, the normal curvature vanish. Yeah, and then, but if you add them, then you got something like this, such a formula which relates the first fundamental form of NS1 or NS2. You take just G1, G2 and subtract them, the components, and then you obtain the normal curvature times the first fundamental form of M. And on the right-hand side, you obtain 2 times this quadratic form, but for the total quadratic form for G. Yes, so you use the same formula. This is the sum of dg1, dg2, but when you obtain this. Yes, so this is quadratic form for G. Okay, and this quadratic form for G has also nice description. Yes, if you, it's easily visible that if you take just this Darboux frame, that in the normal part you take the mean curvature vector divided by its length and E4 orthogonal to it, yes, then it looks like this. And in fact, this quadratic form for G defines the H orthogonal curvature line quadratic forms. They were studied first for general vector by Federico. He noticed this, that this is related, this form is related to it. Okay, okay. And now I'll say, okay, there is also, but you notice that I use all the time this assumption that the mean curvature vector does not vanish. What we can say when the mean curvature vector vanish? It is also interesting points, because when you have this formula, when you have these quadratic forms, they at these points, they are 0, yes, at these points, okay, by the definition. And then you can study it using, because the people studied this Darboushian singularities of this binary differential equations, yes, but we haven't found any geometric interpretation of it. We can write a very huge conditions for several pages, but we don't know what is going on, what is geometry hidden. But the points are interesting, yes, because from each direction, as you remember, if we go back to this theorem when, this one. If we go back here, you see, from each direction, you can go to this point and you find a holomorphic curve which have a high order of contact with our surface. This is due to the fact that the mean curvature vector vanishes, because mean curvature vector also vanishes for the holomorphic curves. Yes, for the holomorphic curves with respect to the orthogonal structure, the mean curvature vector vanishes. Yes. Okay. Okay, so this is just that what we would like to study. We'd like to understand some geometry behind these points, what happens. at these points. Okay. And now I will say some global results which already were published using just the theorem by Saji Umehara Yamada. We can find some Gauss-Bonnet formulas for surface in R4 using just this map G1, G2. Yes, using this map G1, G2, we have the following formula. So this is Euler characteristic, of course, of a surface, and this is Gaussian curvature plus minus normal curvature. Yes, you take the just absolute value of this plus 2 times, and this is just geodesic curvature of this singular set. Yes, in the image. Yes, and you use the just integral with respect to arc length parameter. Yes, so we have such a formula just using the result of Saji Umehara Yamada, and also the other, yes, for the same immersion. So if you take just 1 over p of the Gaussian curvature, yeah, you can relate it to the Euler characteristic of mi plus and mi plan, very defined in this way. Yes. Okay, we have it for each I. Yes, so this is, I wrote 2, but there are 4. Yes, such formulas. Yes, this is the Euler characteristic, and this is the number of positive and negative cusp of GI. Yes, so we have, and this relates the normal curvature to such object. Yes, and in the special case, when M is oriented close surface embedding, yes, satisfying that this is always for generic. This is for generic immersion and generic embedding, satisfying this condition. Yes, so when you have such formulas, I will relate this part mi plus and mi minus with the number of this, the topology of it, with the to the numbers of positive and negative cusp of these components of the Gauss map. Okay, and this is the paper which already published in 24. It collects this result about with these huge calculations, but now we have this new description. Okay, so thank you very much for your attention. Congratulations for the Spanish, and I'm very sorry for the French one. And I really appreciate that both of you came so early after this stressful match. Okay, thank you very much.
Questions?
Okay, thank you. So the second fundamental form of the surface in R4, all the information is contained in the curvature ellipse. Okay?
Yes.
So you consider the curvature ellipse.
We have
all the information is contained. So it's possible to detect these singularities of the Gauss mapping.
You think in the I don't know. I don't know, but yeah, I don't know. So you think the second fundamental in the so if the second fundamental form is contained.
So, for instance, maybe it's interesting to look at a holomorphic curve and look at the curvature ellipse in this case, and then compare with your curvature ellipse.
Maybe you are right. I have to think about it, because yes, this is you have only the contact. You study the contact. Yeah, it should be like this. Okay. Yeah, probably you are right.
Okay.
Yeah, probably you are right. When you have because the only difference between G1 and G2, if it's holomorphic, in fact, this not preserving the orientation is anti-holomorphic. with some, yes, with the same structure. So yeah, you are right. Probably in the ellipse also we will get it. Yeah, yeah, but probably, you know, because if you study without this quadratic form, the calculation is as huge as the contact. Yes, this was our problem, that we get this result. We are very happy that after this calculation we get what we wanted, that something vanished what we expected that vanished, but it was very, very not understandable to understand it. Okay, thank you very much.
Thank you. More questions? Okay, more questions? Now, I have a question. So if you have, everything is local in the sense of one surface in R4, but if you have two surfaces in R4, and you take a pair of weakly parallel points, then we know that from one point, and then the other one, there are lines of weakly parallel points going through them. So we have this new direction, these new lines. Do you think these lines, you know, we can get some by local information, joining these two lines, the information about these two lines and this information about the asymptotic and curvature lines that you defined?
So Pedro just mentioned the project that we worked together. I didn't see the connection, but he saw it. Okay, so I think, yeah, probably you are right, that we can get some information from this weakly parallel using this because this component describe, yes. Yeah, I never thought about it. I never thought that there is any connection with this work, but I see it is. Okay, yeah, probably that there should be something.
Okay.
Yeah.
Okay, any more questions? So let's thank the speaker again.
Thank you.
of the University of Buenos Aires, and she will talk about sparse systems with high local multiplicities.
Thank you. Okay, I'm happy to be here. It's very difficult for me to be here today. One reason is that we have the match today, and most of you are from either Europe or Brazil, our eternal rivals. Yeah, but also because I'm very happy of see all of you here, and we all feel the same, but Cidinha is not with us. So I found this in a video that was recorded not long ago, and she's saying that singularities are everywhere, right? And in fact, she's quoting Hironaka. And it's a very, very nice video you can find on the internet. And I met Cidinha 22 years ago, maybe 23. I was at IMPA, and she invited, I didn't know her, she invited me to come here to Sao Carlos to give a course on the book, as a book by Gelfand, Kapranos, and Levinsky, this size, on discriminants, hyperdeterminants, etc. So I did my best to give a course in 3 weeks about this book. And you know, it is said that the best way to learn something is to teach it. And so I don't know how much the students got from the course, but while giving it, I asked myself the question, if we have a toric variety which is rationally parameterized by monomials, if the dual variety are those hyperplanes that touch your variety containing the tangent space. If this could be also parameterized rationally. Once you ask the question, the answer is easy. But then, okay, I kept this, I wrote 2 pages out of that. And then 1 year after that, there was a conference that I co-organized in Angra dos Reis, a fantastic beach in Brazil. And Bernd Sturmfels was there. And then I told him, you know, last year I was given a course in Sao Carlos, and I realized of this parametrization. I said, oh, why didn't I realize it? I don't know, because you didn't ask the question. And then the following morning, he gave me a page. Well, this is the tropicalization of the parametrization. I need to start learning about tropical stuff. And it ended in my single paper in the Journal of the AMS. So I'm very grateful for Cidinha. And also for me, it was incredible to be here and to feel what Wojtek says, this spirit of joy of mathematics and joy of collaboration. It was a great atmosphere just because of the mathematics involved here and of the people, and the climate here is fantastic. So I am really happy to have known her. And unfortunately, the last time I saw her was on a screen. It was in January 2025. I was at IMSA in Miami, and they gave her a prize, a Latin American prize for mathematical leadership, but she couldn't go there because she was already sick, and she was thanking on the screen. Okay, so let me start with my lecture. So this is the plan. I will tell you which is the main question. I will show you some bounds. I will show you systems with high local multiplicity. I will define this, and I will show you the dual side, and I will end with some questions. So what is sparse system? Sparse system just means that you fix the monomials that are present in your polynomials. Okay, I will deal with n polynomials in n variables with fixed sets of monomials. This could be polynomials of degree d1, d2, dn, for instance. Okay, but you decide which is the monomial structure of each of your polynomials. In our case, I will use the same for all of them. So the input is this set A of m plus n plus 1 exponents in z to the n. And then we'll consider a system of n polynomials with these monomials, fi. And the question is if we can bound the max. So we have n polynomials in n variables. We expect that they intersect at points. So we would like to know, we have one point which is intersection. It is a singular intersection. This means that the Jacobian also vanishes there, which is the maximal multiplicity that this a singularity can have. Okay, this is the question. I think you all understand the question. So what's the multiplicity, I will say then, but it's just the quotient, the dimension of the local quotient by the ideal generated by the Fs. It's just that this, okay? But we cannot evaluate our polynomials at 0 in principle because we could have negative exponents. So I need to understand this at a point in the torus, so with all non-zero coordinates, okay? This is the main difference of what you do usually. You could move the point to the origin, but then I will show you. Our question is in the torus, which is the natural setting for sparse systems. Okay. So when n equals 1, okay, so it is known since long ago that if you have that the multiplicity at one point cannot be bigger than the number of monomials that are really present minus 1. And let me show you why. This is independent of the degree of your polynomial, okay? If your polynomial is constant plus something times x to the 5 plus something that x to the 1 million is independent of the 1 million, the multiplicity cannot be bigger than 1. Okay? So up to multiplying f by a monomial, this will not change when it will vanish at a point in the torus, which is non-zero. We can assume that our exponents lie in the 0, 1D. And then we can take the polynomial x minus p to the d. This has a point p with multiplicity d. But if we expand it, all coefficients are non-zero, right? As soon as one of the coefficients is 0, the multiplicity cannot be d. It has to be smaller. And it is not difficult to give a point. This was first observed by Hajos, I don't know how to pronounce it because it's from Hungary, in 1953. I didn't read his paper, but I believe that he did it. And it is easy to give a proof because it's easy to see that if we have a point, this is an f, and we have p is a root with multiplicity mu, then this vector, something's happening. This is not working, right? Up. Well, the vector C0, P to the 0, etc., has to be a non-zero vector in the kernel of the van der Mondes matrix. And then it's easy to see to get a non-zero vector in the kernel, you have this bound. Okay, so in this sparse setting, it is known which is the maximal number of points that could be in the intersection, okay? This is if you have polynomials of degree d, the standard number is the Bezout number, is the product of the degrees. But if you don't have all the monomials, then it is known that if you have polynomials with this support, then the maximal number of isolated points in the torus counting multiplicities is at most what is the normalized volume of A. This is n factorial times the Euclidean volume, assuming that the span of A has dimension n, that the affine dimension of A is n. And generically, there are these many simple solutions, okay? As I say, this is a special case. This generalizes the PKK bound, and it is in general much smaller. So we already have an upper bound. So if the multiplicity at one point cannot be bigger than this number, that the integer volume of A. So A, this means the volume of the convex hull of our points, okay? Okay, let me give you a small example. So let's consider this system here. This starts and then disappears. So we have the system up there. Then to have this system, there are two informations. One information is this matrix C of coefficients. The second information is which are the exponents. So if I give you A, which are A is there, 0, 0, 2, 0, etc., 1, 3, these are the exponents in our monomials. I give you the exponents, and I also give you the matrix of coefficients. And this is the information about the system, right? Then, so the system can be written as C times these vectors monomials as a column. So in particular, this vector of monomials needs to lie in the kernel of the matrix C. Right? So in this case, the Bezout bound, so the first polynomial has degree 3, the second has degree 4, the Bezout bound is 12, and this big AK bound is twice the Euclidean volume of this object. This yellow thing here is the convex hull of our points, and it has volume 8. So at most, a solution and not 12, okay? So the question, as I said, is can we bound the maximum local intersection multiplicity at one point in the torus in terms of the dimension, which is n, and the codimension, which is m. So the number of points is n plus m plus 1. Okay, n is the dimension. I'm going to call m the codimension. And the number of points, I will say it again, is n plus m plus 1. So as I said, this equals the vector space dimension, the local quotient by the ideal generated by the f's, a local quotient at the point q. And there has been a first upper bound that was given by Gabrielov in 95. So he proved that this intersection multiplicity cannot exceed this number. It's 2 raised to the combinator. This is just like n squared, n times n minus 1 over 2. This behaves like an n squared times n plus 1 to the n, where n is the number of monomials. So what is interesting again is this does not depend on the degree of the polynomials. It just depends on how many monomials and which is the dimension and the codimension. But it is big. Now you have this number here. What we are going to do is we are going to add some hypotheses and we will somehow delete these 2 to the n2. Okay? Okay, so what we're going to use this combinatorial tool, which is the mixed covolume, which with a different name was in a poster I saw yesterday. So I read about this for the first time. There was a paper by Rafael Villarreal from Mexico, and then there was a paper by Bernard Tessier that appeared multiplicité, volume, I don't know, but it was not published in a journal as he used to do. But I don't know who, I want to ask Bernard who was the first idea. Probably this comes from the Russians. So we look at all the polyhedra such that at each point, so you are used to this if you studied Newton, at each point you put a non-negative orthon at each point, and then you look at what is behind, okay? So you need to ask that this, your set is such that the complement is bounded. It needs to touch all the hyperplanes because you want to have someone below which is bounded. So here my points are given by this 1, 1, 3, 0, 0, 3, and here there's another point at 2, 1. So the blue part, if I take this is what's called the Newton polytope of the polynomial with these monomials. The green part is what's called, these 2 segments there that are seen from the origin is the Newton diagram, and the green part is going to be the mixed covolume. Okay, if I take 2 polynomials with this same picture. So again, I'm saying again what I have just said. So I have a polynomial with these monomials. Probably this was x1 square, x2, but I forgot it. So this BD is the convex, this green thing below, which is not convex. And the mixed covolume is twice, again, 2 times the Euclidean volume. This 2 is because we want to have that the simplex has volume 1. So the simplex in Rn has volume 1 over n factorial. So the integer volume is n times that, which is 1. Okay, so here I have 2 polynomials that I have not written for you. So I'm not writing where the monomials are. The monomials are from there up to that part. So one of the monomials has exponent 2a, 0, and the other one 0, a, and so there are some other ones upstairs. The Newton diagram is this line, and the corresponding bounded part is in red, and same for the other one. So these are just the boundary monomials of F2, and the Newton diagram is this segment plus this segment, okay? And the mixed covolume is the volume of this area downstairs. So you take what's the Minkowski sum, all points that are sum of 1 point in the first plus 1 point in the second one. And then you are going to see the volume of the first part, the second of the second unbounded part, and what's left, this is the value of the mixed covolume. Okay, so there is a known theorem which says that the mixed covolume is a lower bound for the local intersection multiplicity at the origin. So now look that I change from my small f's to capital F's, okay? So I given capital F, they have an intersection point of intersection singular. They have an isolated intersection at the origin, and the multiplicity is at least is bounded below by this mixed covolume, okay? And if the system is non-degenerate at the origin, then equality holds. What does it mean to be non-degenerate? Well, the first thing that we need is that F is convenient. We want that each of the monomial supports touch all the edges so that we have something bounded below. We don't want to have infinity. And also, we need some degeneracy at infinity. So what we need to do is we need to look at parts of the corresponding Newton diagrams. For instance, here, this segment and this segment they are parallel. Each time this happens, if you restrict they are essentially polynomials in one variable. So we need to ask that these polynomials in one variable do not have any common root in the torus, so that the resultant should be non-zero. Okay, so we need to ask that at each time that there is a possibility to have a non-zero solution corresponding to parts of the Newton diagrams of the different polynomials, we ask that there are no solutions there. It's like having no solutions at infinity. Okay, if this happens, then we have equality. But it is not easy to control non-degeneracy. I will show you. And if the Newton diagrams are fixed, this can be controlled. You can use a computer algebra system and find what's called the phase resultant and decide. If I give you numbers, you can decide whether it is the case or not. Okay? And of course, I am using this for polynomials, but this holds for the power series too. It's just a local statement. Okay, so I start with my small f's, and I start with a point Q in the torus. So there is an obvious way to move it to the origin. So I consider the polynomials capital F's, just given, here it should be Fi, not F1, just f of x plus Q. We can do it, but look that we are losing sparseness. Okay? We can do this and move to the origin, but now the information of the exponents is in the coefficients. We have to get track of the fact that we lost the information of the exponents, and we have it in the coefficients. But and it is easy to see that we can assume without loss of generality that Q is equal. So it's easy an argument, but let me skip it for now because we have this torus action, we just can move it. And then when Q is 1 or when Q is an integer, the first result that we found is that if we want to find a system which highest local multiplicity is enough to look at systems with integer coefficients. So we don't lose any information to find the maximal possible multiplicity if we consider a system all whose coefficients are integers. Is this clear? It is not difficult, but it needs a proof, a one-page proof, okay? So this is what I'm going to do. So here I'm going to present a very explicit system with high local multiplicity. And the system is as follows. So we are going to have, so remember that we have n, the number of variables, and m, the codimension. So I'm going to have n polynomials of like this, from m plus 1 to m plus m. For any d, this is our polynomial. So we have these binomial coefficients, these signs, and if we put here x to the k, we would have x minus 1 to the d, right? But on this side, look at the exponents. The exponents are k, k squared, k cubed, up to k to the n. Okay, so the trick is that the exponents lie in what is called the rational normal curve. Okay, this is the system. And all the supports are contained in the support of this polynomial, and the codimension is m. Okay. So what's the theorem? The theorem is that if we look at this common intersection, then there is a common root, so there is a point of intersection. This one means the point 1, 1, 1, 1, right? We are in n variables. And the multiplicity is at least the combinatorial number m plus n. And we conjecture that the multiplicity indeed equals this combinatorial number, and we prove it for n equals 2 and any m, and I will try to show which is the difficulty to prove it in general. For n equals 2 and any m, so this Newton diagram that I had shown to you before corresponds precisely to F1 and F2 here. So first, what we did is to find high local multiplicity. We started with polynomials which already had the highest possible multiplicity at the point 1, 1. So you see, here, this is F1 equals 0, and the point there with many branches is the point 1, 1. And here, this is the F2 also. Again, there are many. It's a very singular point. We start with two polynomials which already have at 1, 1 the highest possible multiplicity, singularity. So the both hypersurfaces are very singular, and moreover, the intersection is tangent, it's not transversal, okay? But now we need to prove that the system is non-degenerate. So it is easy to see that it's convenient, that it touches the edges. But then we need to see that the restriction to the red segment of the first polynomial and the restriction to the blue segment of the second polynomials don't have any root in common. And it's hard to do it for any n, okay, or for any m. So what we did is we found a paper of people working in hypergeometric functions. And it happens that our polynomials are two specific hypergeometric polynomials. And it was proven by the people in this other community that these two polynomials interlace. Interlace means that here are the roots of one of them, and the other ones are just in the middle. So two are here and one is in the middle. In particular, they are different. They don't have roots in common. But we needed to use what had been done by the people in this community, because we had particular coefficients, but for any m, it's very hard to decide that these two, even univariate polynomials, do not have a common root in general. So if I give you a particular instance, I can do it. You put the computer and we check the result. Okay, so the first bound that we found, sorry, I missed. I used to have a standard watch, but now it's broken. Okay. So the first bound that we have is, let's look at the statement. So it says that this TL is essentially if all the L coordinates are different, this is just m plus n. And if the all C coordinates are non-zero, this is just again m plus n. But if some are 0 or some are not different, this number can be lower. But essentially, this is the local multiplicity is at most the minimum between these two products. In particular, if there are no repetition in the A's and no C equal to 0, this gives the hypothesis that the local multiplicity, if the system is non-degenerate, is at most n plus m to the n, which is already much smaller than Gabriel was bound, but he didn't have the hypothesis of non-degeneracy. We forgot about this 2 to the n2. Okay, so in the case of a circuit, what is a circuit? A circuit is, sorry, a minimally affinely dependent set. In dimension 1 is just 3 points on a line. In dimension 2 are 4 points, so that no 3 of them lie on a line. There could be the vertices of a quadrangle, or there could be vertices of a simplex plus 1 more point inside. But the point cannot be on any of the edges, otherwise this would be already affinely dependent. So a circuit is, you have n plus 2 polynomials which are minimally affinely dependent. So, and this is, in this case, the bound that we get is n plus 1, and it's really attained. So it's easy to see that it is attained. I will show you. And so here, this is a picture of the cyclic configuration. We have this curve t squared t to the n, that this is the k squared k to the n in the exponent. So these points are these points. I'm sorry, I cannot point with this. It is broken. So are the points on this part. And this object is the convex hull of the points. Okay, so when m equals 1, when the codimension is equal to 1, so we get the bound m plus 1, and the question is, when is this bound attained? For which configuration? So we say for any configuration which n plus 1 plus 1, n plus 2 points, then the maximum multiplicity is n plus 1. But it depends on which is A to be able to get to n plus 1. This depends on the combinatorics of the exponents. Okay? It not only depends on the number of points, but also in the combinatorics of the exponents. If we want to get highest multiplicity on the plane, we need the 4 points to be the vertex of a quadrangle and not having 1 point inside. But moreover, it is attained if the following happens. So I will try to read only what is necessary here. I'm sorry, I cannot point. So we have a set of codimension 1. This means you have points that span something of dimension n, and you have n plus 2 of them. And we have a matrix of coefficients. What does it mean to be? Hold on. Oh, thank you. Hold on. No, but I hold on, it doesn't work. Try it. Does it work? No, it does not work. Ah, I have to press. Okay, I will press. How do you press? I cannot.
But I have to connect it to pass this line.
Okay.
Você conecta lá?
Thank you.
You have to pass it to the point with this.
Okay. I will do my best. At least now I can point. Yeah, okay. So we assume that 1, 1, 1 is a solution. So what does it mean that the matrix is uniform? It means that all the maximal minors are non-zero. So I look at the matrix of coefficients. In order to get the maximal number of solutions or the maximum multiplicity, is a natural condition that acts that all minors of the coefficient matrix are non-zero. This is the meaning of uniform, okay? So I have this matrix, the system with uniform matrix, then it will have at this point multiplicity n plus 1 if and only if A is affinely equivalent, so up to a linear affine transformation, invertible linear affine transformation, has to be equivalent to a cyclic point configuration. And this cyclic point configuration is not any. It depends on the kernel of C. So it has to be affinely equivalent to a cyclic configuration, the image by this map gamma, that sends t squared, etc. And the points are related to the kernel of the coefficient matrix. All this needs to happen to get maximum multiplicity. And okay, this is working. And in this case, so you will see how did I land into this question? I will show you later, but we really wanted to have system of sparse polynomials with the maximum possible number of real solutions. In fact, we wanted positive solutions and wanted real. So the idea is easy. So it is easier to find points with high multiplicity because this means derivatives have to vanish. So this is given by a zero condition. This is 0, this is 0, this is 0. Not any 0 could happen. This is what we are trying to describe. But this is easy to find points with high multiplicity that have a system with many real roots. But the idea is you have a point with multiplicity m. Over the complex number, you just modify a little bit the system. Instead of f equal to 0, you put f equal to epsilon for n generic epsilon, and you're going to get m isolated simple points. But the question is how to deform the system to have all these point reals. We really wanted to have many real solutions. So this is why we started looking at points with high multiplicity at 1, 1, 1. If we perturb a little bit, then if they are real, they're going to be positive because they will be close to 1. Okay? So, yeah, I have to go back. Thank you. Wow, a lot here. And it happens that in this case, in the circuit case, it is possible to perturb the system and have n plus 1 positive solutions. But the proof is using what's called the descent d'enfant, and it is absolutely non-constructive. So we don't know how to do this in a constructive way. But we proved in this case that it is possible using this tool that was first defined by Grothendieck. Okay. And then consequences, okay? The first consequence is the following. If you look at our bounds, if all the coordinates of your points are between 0 and this, I mean, our configuration A is contained in the cube 0d times 0d times 0d, then what we proved that if the system is non-degenerate, the multiplicity can be at most d to the n. Okay, but this is much, much smaller than the volume of this cube, which is n factorial d to the n. It's much smaller than the total number of solutions. It's just only d to the n. It's n factorial times smaller. So if we take m equals 1 and n equals 2, for instance, we can take this support, 0, 0, 1, 0, 0, 1, 1, 1. You see any coordinate goes from 0 to 1. So d is equal to 1 here, okay? And now, so what is a polynomial with this support? This is just a hyperbola. It's a number plus something times x times something times y plus something times xy. So here, there are two of them. One is the red one, and the other one is the blue one. And it happens that they intersect. In general, they will intersect at two real points. They have degrees 2 and 2. The Bezout number is 4, but indeed the number of points of intersection, not at infinity, is at most, over the complex number is at most 2. And here we have a real intersection with these tangents. The multiplicity cannot be 1, is 2. So we get that the multiplicity is 2, which is bigger than 1 to the square. So we get a bound which is above the bound that we get in case the system is non-degenerate. So it cannot be non-degenerate. So how do we do? This is a very easy case and we cannot treat it. What do we do? So what we did is to move to what's called the Gale dual system to address these cases. So what's the Gale dual system? So we are going to move from a system in n variables and codimension m to a system in m variables, codimension many variables, okay? I will say it again. We are going to move from a system of n polynomials in n variables to a system in m variables. And we have a point of intersection with the same multiplicity. It's a little bit, for me, each time I think of it, it's a little bit surprising. So you go from n variables to m variables. And this is an isomorphism of tori. I will show you in a while. What was the torus here is we are outside the coordinate hyperplane equal to 0, outside xi equal to 0. And we are going to move to m coordinates outside some m hyperplanes equal to 0, other hyperplanes, okay? And then we start with our matrix A. This is A0, n plus m, are vectors of length n, but I add a row of ones. If I add a row of ones, now the kernel of the matrix A is not just the kernel of A, are the vectors in the kernel that add up to 0. So these are the affine linear relations between my point. So what is important, if one point is in the middle of two other ones, I don't care where they are. Okay, so this will give us the affine linear relations of our points. And what's a Z Gale dual matrix? We take a matrix B whose columns generate the integer kernel, but then I'm going to look at the rows of this matrix. I will say it again. We take a matrix B whose columns generate the integer kernel of A, but then are going to look at the row vectors, which are vectors in dimension m. These are going to be called B1. I don't know the name. I'm going to give them. And then again, I take a Gale dual basis. I will be very quick. If you want, we can discuss this later, but I will try to be quick. So then we also take a Gale dual of the matrix C. Again, it's a matrix whose columns generate the kernel of C. And up to changing the basis, we can assume that the first column is all given of ones. So now to each row of D, we are going to assign a linear vector, a linear function in new variables that are called Y. So the coefficients here come from the row vectors of a matrix whose columns are a basis of the kernel of C. Okay? And then I need to raise these linear functions to these numbers. These numbers are given by this basis of the kernel of A. And if we are outside the union of the hyperplanes pi of y equal to 0, then there is a fantastic algebraic isomorphism between where we started with n variables and here with m variables. And we started with the zeros of the f's, where coefficients c and exponent a. And then we need to look at the solution of these rational functions equal to 1 here. You can clear the denominator and put the positive ones on one side, the negative ones there, and look at this polynomial equal to 0. This is a polynomial where these are not variables, these are just linear functions on the y variables. And this system has an intersection point with the same multiplicity as our original point. And then what happens is that we use our bound. Our bound said n plus m to the n. But now if the Gale dual system is also non-degenerate, we get the bound n plus m to the m, not to the n. This is the number of variables. And then if both systems are non-degenerate, we get this bound, which I love it because it's symmetric in m and n. It's n plus n raised to the minimum between m and n. And we think that this is true. No, we still that it is even smaller than this. And then we found a new local dual system that we really I really don't understand it. And it's like this. So we define another system which has as coefficients the elements in the kernel of A, and as exponents, the exponents are given by the matrix in the kernel of C. It's very strange. So we started with A in the exponents, C in the coefficients. Now we put as coefficients elements in the kernel of A, as exponents things that I read in the kernel of C. It somehow interchange coefficients and exponents. And if this new Gale dual system, the Gale dual system and this new are both convenient and degenerate, then they give the same multiplicity. And so this is in n variables, the two others are in n variables. So for me, it's I see the proof, but I still don't understand it, but it's true. I hope that our proof is true. So if we call m of nm the highest possible multiplicity at a non-degenerate multiple point in the torus of a Laurent polynomial system in n variables and codimension m, we have a support fixed with n plus 1 points. So we don't know, this is a question, is it true that this is symmetric in m and n? And we really think that, you remember that the multiplicity that we found for this special system, at least for n equals 2, or when m equals 1, is n is the combinatorial number m plus m n or m plus n m, which is symmetric in m and n. And we really think that this is the upper bound, but we cannot prove it in general. And the question is, for which configurations A? I showed to you the statement, I didn't show you the proof, that in the case where m is 1, it has to be essentially a cyclic configuration. So in general, for any m, which are the configurations for which the maximum multiplicity can be attained? We don't know. As I said, we expect that the combinatorics of A will impose the restrictions on the multiplicity. And then, sorry. Oh. So as I said, we were led to this paper because we wanted to find many real solutions. So the question is it possible to find a small perturbation of the coefficients such that starting from these many, the multiplicities at least this point, to find at least these many real solutions? So as I said, we can prove it for the sand and fun, but we don't know how to do it in an explicit way. In general, it is unknown. And moreover, it is not only unknown, it has been proven that if you have many real solutions, your coefficients need to be very close to the discriminant. They have to be very close to a system which is singular. So in fact, even numerically, it's going to be unstable. If you have heard about condition numbers, etc., to solve numerically a system is going to be horrible because you need to be close. So it's not also a difficult algebraic question. It's also a difficult numerical question to find many real solutions. Okay, let me try to see if I can go to the website. Can you do this for me? Go to the example. I cannot, but I'll show you the example. You can do it? Okay. But then we will need to go back. Okay. Here. No, one more. One more. Yeah. Okay, hey. No. Not so much. Just. Okay, I will do it. I will do it. Okay, I will do it. So let me show you this example to show you the difficulty. So we consider the system a family of polynomials. The family is x4 minus x squared plus cx plus d. There are only two variables here, c and d. Okay, it's an easy thing, polynomial of degree 4 in one variable. I fixed two coefficients. I am only moving two coefficients, c and d. And then this red picture that you see there is discriminant equal to 0. What's discriminant equal to 0? This is the discriminant. This will vanish whenever there is a multiple root. Wherever this polynomial has a root, where the derivative also vanishes. So the red thing here is discriminant equal to 0. If you are there, the polynomial with these coefficients will have at least a double root. So in general, in all the regular points of the discriminants, there will be one double root. At this point of intersection, there will be, this is a transversal point of intersection of the discriminant. There will be two different double roots. So the polynomial will be of the form x minus a to the b times x minus a squared times x minus b squared, two double roots. And if we are here, we will have a triple root. We have x minus a cubed times x minus b. So, but this is a cusp point of the discriminant. So this is a simple singularity of the discriminant. This is a cusp point of the discriminant. I have a point with multiplicity 3, and it is a bad singularity of the discriminant. Here in this picture is as bad as it can be, okay? Because this is a transversal intersection of two branches, and this is a cusp. And what happens is that the number for coefficients in the green region, in each of the connected components of the complement, the number of real roots is the same. This is easy to prove. So here there are 0 real roots in the pink region. Here in the white region, there are 4 real roots. You see that it is a small region and it can be even smaller. So in this small part, there could be 4 real roots. Here, 0. And all here, there are 2 real roots. Here, 2 negative, here 2 positive. And if we cross the axis, there is 1 positive and 1 negative. But so if we are here, we can move in all these directions. Yeah, I have a point which is a double root. I move it in this direction, I will get 2 roots. But if I move in this direction, my roots are going to be complex. If I here the same, from in this direction, if I move the coefficients CD in this direction, so I take a point CD here, which corresponds to a polynomial. If I move in this direction, I will get out of a double root 2 simple roots, real. In this direction, I will get complex, but I have an open set of directions where to move. And here, even here, I can move in all these directions, I will get 2 roots. And if I move in this small direction, I will get 4. Both of them will given real after the formation. But here, if you move in any direction but this tangent direction, you're going to get complex roots. So here I start with a triple real root. But if I move my coefficients in any direction but this one, I'm going to get complex roots. The only way in which can move my multiplicity 3 root and this perturbate to have 3 real roots out of it is I move in this direction. Just only one tangent direction to move to get real roots. You see it? And this is what I am describing here with a bit more detail, but it's essentially what I just told you. So it's a difficult question. Let me try to go back if I can. Okay, I did it. So I'm almost ending. And so the last question that we have, so we are also trying to bound, there are many symmetries. So we also bounded the highest number of positive solutions of a system supported in a circuit. And it's the same number n+1, which is the maximal local multiplicity. And something, and there are other bounds. where the maximal number over the complex numbers equals the local multiplicity over the real numbers. And we wonder if there is some mathematical results behind that. We try to mimic like a kind of argument in 2 dimensions using tropical things, but we are not sure, but it's kind of intriguing, and we ask whether there is some relation. This is all I wanted to tell you. Thank you very much for being here.
Are there any questions or comments? There's one.
Just a short question. Like when you were saying about this duality in the Gale dual systems,
Yes.
right?
Yeah.
So this duality that came, like it changed the coefficients into the.
No, not exactly. The standard Gale duality does not change the coefficients. It just
Yeah, but then
give you
afterwards.
these polynomials, but so still the exponents are related to A because the B's are in the kernel of A, and this is related to the kernel of C, but still you have here the coefficients and here the exponents. But we found this other system
This one,
where this is switched.
But this system works for any non-degenerate, or in the special case here that you had this this sequence with the highest multiplicity.
No. This is always.
Always.
This is always, except that for the Gale dual system, we know that the multiplicities are the same. And in this case, the multiplicities need not be the same. They are the same if they are non-degenerate.
But still. Okay, thank you.
So these two always have the same multiplicity, and this multiplicity is bigger or equal than this one, I don't remember. But it can be equal if they are not all non-degenerate. But for me, it's like kind of very mysterious.
I agree, that's why I'm asking. So like, what's the kind of a proof of that fact?
The proof is not difficult at all. So we can take a look together.
Okay, great, thank you.
You're welcome.
Any other questions or comments? No? Well, if not, we thank the Cidinha. Okay, so our last speaker this morning is my former PhD student and also a very dear friend, Daniel Duarte of Center of Mathematical Sciences of the UNAM, Mexico National Autonomous University. And he will talk about singularities of matrices and determinantal varieties.
Yes. Okay. So thank you, Mark. Thank you for the introduction, and thank you all for being here in this third talk in a row this morning. Okay. So also thanks to the organizers for the invitation. It is truly an honor to speak in this workshop, especially on this occasion since it is dedicated to the memory of Cidinha. Okay. So as my own I have it here. As my own personal homage to her, I decided to use this title, Singularities of Matrices and Determinantal Varieties, which I deliberately stole from a talk that she gave in Mexico in 2014. Okay, and here is the first slide of that talk. Okay, so as you can see, this took place in Mérida, in Mexico, in December 2014. Okay, and I'm pretty sure that several people in this room was in that conference. Jean-Paul for sure, Juanjo, and several people, José Luis maybe, but I was not in that conference. No, I several years later, I really don't remember why or how it happened. I saw the video of this talk because you can find it on YouTube. So I saw the video, okay, and in this video, well, she talks, of course, of different aspects of singularities of determinantal varieties, okay, as you can see in the second slide of her talk, okay. Now, so when I saw this, I got very interested in the talk because I realized that she was going to talk about Nash blowups, okay, which is a topic that I have like very close to my heart. And so I saw the video, you know, with great interest. And some years later, again, I met Cidinha once again in Mexico, and I asked her a bunch of questions of her talk, of this talk she gave in 2014. As usual, she was very kind, no, very patient. She answered all my questions. And at some point she said, let's continue this conversation in Sao Carlos. So she invited me to come here for the first time in my life. And we continued talking about it, discussing Nash blowups, determinantal varieties, and those discussions eventually turned into collaborations. Okay, first with her and Thais Dalbello, and later also with Danilo da Nóbrega. Okay, so and it is the results of those collaborations that I'm going to talk about today. Okay, so I'm going to present two theorems on singularities of determinantal varieties. Okay, so now I'm going to write both theorems. Okay, and I won't define anything for the moment. I will do it as during the talk. So let me just give you the statements, and then I'll give details along the way. Okay, so the first one is about Nash blowups, precisely. Okay, the first one is, it states, or it says that over positive characteristic fields, the Nash blowup of this generic determinantal variety is non-singular. Okay, so in other words, by applying once the Nash blowup in positive characteristic, you obtain a resolution of singularities of these varieties. Okay, so this is the first result. It was a collaboration with Cidinha and Thais. And the second one is a little different, okay, is a collaboration with Thais and Danilo da Nóbrega. And in this result, we studied symmetric generic determinantal varieties, okay? But in this result, what we did was to study some functions, okay, non-degenerate polynomial functions. And what we did was to provide formulas, explicit formulas, I will show them later, for the Euler characteristic of the Milnor fiber of such functions, and also of the Euler obstruction of this variety. Okay. Now, these two theorems may seem like quite different, and they actually go in different directions, but they do have something in common. Okay, the objects we study, okay, the symmetric variety and the generic symmetric determinantal variety, they are both determinantal varieties and also toric varieties. Okay, so it is in the interaction of these two structures that lies the key for studying these two questions. Okay, so let me start right there. Okay, by recalling the basic definitions of these determinantal varieties and also of toric varieties. Okay, so let me start right there. Okay, so I first recall definition of a toric ideal and a toric variety. Okay, so let me denote as a finite set of vectors, okay, in C to the D. Okay, now with these vectors, we can define a monomial homomorphism, okay, so going from the polynomial ring in n variables as much as this set of vectors, and we go to the Laurent polynomials, okay, TD plus minus. Okay, and what we do is to associate to each variable the corresponding monomial, okay, the monomial corresponding to each of these vectors. Okay, t to the gamma I, here I'm using multi-index notation. Okay, so this defines a K-algebra homomorphism, so we can take the kernel, okay, of this map. Okay, so now we have a set of binomials actually, and we denote this as IA. Okay, and then we denote as XA the zero locus of this ideal, okay, sitting in K to the N. Okay, and this is what we call a toric variety, or the toric variety defined by this set of vectors. Okay, there are many different definitions of toric varieties. This is the one I'm going to use. Okay, now an important remark I want to emphasize is the fact that any prime and binomial ideal is of the form IA. Okay, so whenever you have a prime ideal generated by binomials, then there must be some set A, and such that that ideal corresponds to this IA. Okay, this is important for us. Okay, so this is the toric world, the toric side. Now, let me go to the determinantal side. Okay, so okay, first the generic determinantal varieties. Okay, so let me denote as L a matrix whose entries are variables, distinct variables. Okay, where I goes from 1 to m, and j goes from 1 to n, okay, where all xij's are variables, okay, xij variables. Okay, then I'm going to denote as A sub t the ideal generated by t times t minors, okay, of L. Okay, this is a determinantal ideal. And the variety defined by this, MTMN is the usual notation that actually it was already introduced by Helen in her talk. Is the zero locus of this ideal, okay? AT, sorry, in KMN. Okay, and this is what we call a generic determinantal variety. Generic determinantal variety, yeah. Okay, so this is the first one, and the other one that we will consider are the symmetric determinantal varieties. Is essentially the same, except that we consider a square matrix, also of variables, but symmetric. Okay, so let me note as L tilde Xij. Okay, this time is square matrix. And what we know is that Xij is Xji. Okay, it's a symmetric matrix of variables. And as before, okay, I denote as Bt the ideal generated by t times t minors of L tilde. Okay, and the Stn. This is how we would denote the zero locus of this ideal. Okay, and this is what we call a symmetric, generic symmetric determinantal ideal. Okay. Now, just by definition, if you consider t equal 2, okay, this one and the other one as well are binomial ideals, okay, whenever t equals 2. We also know from the determinantal theory that these two ideals are prime, okay? So these two are prime binomial ideals. Because of this remark, they should be also of the form IA for some set of vectors, okay? So let's find A and B such that the corresponding toric ideal is this one and this one for t equal 2, okay? This is this is our first step towards these results, okay? Okay. Now, I'm going to show you, okay, so let's find these sets A and B. I'm going to show you how we did it for this, only for this one. The other is pretty similar, okay? So I'll explain how we did it in an example, okay? And actually what I'm going to explain in the example is the strategy, the general strategy for proving the fact I want to explain. Okay, so example. Okay, so let me consider the case 2, 3. Okay, this is the zero locus of 3 binomials. Okay, where they correspond to the minors of this matrix. X1, the 2 times 2 minors, X1, X2, X3, X4, X5, X6. Okay, and these F1, F2, F3 are the 2 times 2 minors of this matrix. Okay. Okay. So what is the set A that we're looking for? Okay. Now here, after computing several examples, you know, finding different candidates, etc., we arrive to the following set of vectors. Okay, E1, E2. E3, E4, minus E1 plus, minus E1 plus E2 plus E3, and minus E1 plus E2 plus E4. Okay, this is a subset of Z4, and the EI is the canonical basis. Okay. Now, so we got to this, right to this set of vectors just really by doing examples and, you know, trying different combinations, etc. Okay. Now, once you know you have this set of vectors, how do we prove that the toric ideal corresponding to this one is the same as the ideal generated by these minors? Okay, let me do it here. Okay. So these vectors are defined, constructed, so the following inclusion can be easily verified. Okay, so A2 is the ideal generated by F1, F2, F3. Okay, so because how these were defined, we can prove very directly, straightforward computation, that this one is contained here. Okay, okay, this is because everything is explicit. You take the generators, see the kernel of the corresponding map, and just check that the kernel, they belong to the kernel, okay? Straightforward computation. But once you know this, you take the corresponding varieties, okay? So this one is contained here. Okay, so the toric variety is contained in the determinantal variety, and because of the determinantal theory and the toric theory, we know the dimensions of these two, okay? In this case, they have dimension 4, okay, the 2 of them. And we also know that they are irreducible. So they must be the same, okay? Okay, and because they are prime ideals using the Null-Stellen sets, you conclude that this one is A2, okay? And this is exactly the strategy in the general case, okay? We have a completely explicit set of vectors, okay? And so the set of vectors is constructed for this to happen, and the rest of the proof is exactly the same, okay? Now, This is regarding the generic determinantal variety. For the other one, it's very similar. I mean, these vectors are a little different, but the strategy is the same. We know the dimensions, we know they are irreducible, etc. Okay? So in general, these sets looks like this. Okay, this is for the generic determinantal variety, and this is for the symmetric determinantal variety. Okay, so these are the general expression for these vectors. Okay, so far so good. Okay, so now let's talk about the first theorem. Now that we have the combinatorics, okay, now that we have both the determinantal theory and now we have the combinatorics to do the combinatorial study, now we can go to the questions. And we first, let me start with the Nash blow-up, okay, with the theorem on Nash blow-ups. And for that, okay, okay, let me recall the definition. And I think this one, yeah. Okay, good. Okay, so recall we want to prove that the Nash blow-up of the generic determinantal varieties, two generic determinantal varieties, is smooth. Okay. Okay, so let me first recall the definition of the Nash blow-up. So we start with an irreducible variety, okay, in K to the n, okay, of dimension d, okay, irreducible, and we assume that the field is algebraically closed of any characteristic. Okay? And then we consider the Gauss map, which already appeared this morning. So in this case, the Gauss map is defined as follows. So we remove the singular points, okay, and then we go to the corresponding Grassmannian, okay, GDN, and what we do is to associate to each non-singular point its tangent space, okay. So this is only for non-singular points, okay. We take the graph of this, the graph of G, okay, sitting in X times the Grassmannian, okay. And then, this is just a subset here, we take the Zariski closure of this subset, and we denote this as X star, okay. Here we have a projection to X, we can restrict this projection to this subvariety, and the couple X star nu is the Nash blow-up of X. Okay, so this is the definition. Now, what's behind this definition is roughly speaking, is the possibility of studying singular points, okay, by looking at the tangency on nearby points, okay? So in the Nash blow-up, a singular point becomes or gets separated in terms of all possible ways of approaching the singular point tangentially, okay? So this is kind of the idea behind the Nash blow-up, okay? Now, so the first interest, so this was firstly introduced as a possible method, potential method for solving singularities, for the problem of resolution of singularities. Okay, so the question, okay, that is usually attributed to John Nash, but it also appears in the work of Semple. Okay, the question is, so you start with this variety, okay, and then you apply the Nash blow-up. I mean, this usually has singularities, again, not for the generic varieties, the determinantal varieties, but in general, this continues to have singularities, okay? So you do it again, okay? And so on, okay? So the question was whether a finite iteration of this process gives a resolution of singularities, okay? This was the question. Of course, nowadays, we know that this question is false, okay? Last year, or a couple of years ago, we found counterexamples in dimension 4 and higher. I think that Max Layton will talk about this on Friday, okay? But in the time we were discussing all these with Cidinha and Thais, there was no counterexamples. Okay, so there was still hope. Anyway, so we were discussing this question for determinantal varieties. Okay, now precisely in Cidinha's talk, she presented the following theorem that was also mentioned by Helen, that it says that in characteristic zero, okay, over the complex numbers, if you take the Nash blow-up of the genetic determinantal varieties, okay, for any t, okay, this is not singular. Okay, so you just need one step to get the resolution using Nash blow-ups. Okay, and so in those days, those years, we were starting to work in positive characteristic. Okay, this question, but in positive characteristic. And so we decided to try, okay, this result in positive characteristic, but in the toric case, because there we have some tools that I will explain in a moment. Okay, so that was the reason to consider the case t equal 2. Okay, and so with Thais and Cidinha, we were able to prove the same statement, okay, for t equal 2 in positive characteristic. Now, regarding the proof, okay, of this theorem, we didn't actually give a new proof of resolution of singularities. What we did, what we noticed is that in this case, okay, this very particular family of varieties, we noticed that the problem of resolution of singularities in characteristic zero, iterating Nash blow-up, is equivalent to the same problem in positive characteristic. Okay, for this family, it's the same to solve the question in characteristic zero than in characteristic P. Okay, this is what we noticed. And so, because Evelyn Gussain said as result, okay, our theorem is deduced. Okay. Now, how do you prove such a thing, right? That it doesn't depend on the characteristic. Okay, so let me explain this. Okay. Okay, so it all comes from the fact that, as is usually the case in toric geometry, the Nash blow-up has a combinatorial description. Okay, now in general, the combinatorial description do depend on the characteristic, but in this case, it doesn't. Okay, so let me show you how and why. Okay, let me erase this as well. Probably, or maybe. Okay, I'll leave it there. Okay, so first we need to turn the problem of resolution of singularities using Nash blow-ups for toric varieties to a combinatorial problem. Okay, so this is the first step. Okay, so combinatorial description of a toric variety, and then you apply the Nash blow-up. Okay, the Nash blow-up of a toric variety. Okay, so let me give you the combinatorial ingredients for this. So, okay, as before, recall that in order to have a toric variety, you start with a set of vectors. Okay, okay, in C to the D, and here we ask that the group generated, the lattice generated by A must be all of C to the D. Okay, this is not a restriction actually. It's just to know that the toric variety has dimension D. Okay, so this is not really a restriction. Okay, now, okay, so the toric variety lives in K to the N. Okay, and let me denote as P. Usual, the characteristic of the field, including 0. Okay, it could be a prime or 0. Okay, now, with this information, denote as MP, okay, the following set of vectors. Okay, let me write it and then we'll discuss it. Okay, I'm going to take the sums of all D tuples. Okay, D tuples. I take the sum whenever the determinant of these D tuples are not 0 mod P. Okay, if P is 0, well, just ignore this part. Okay. Okay, so what is this? So we have like bunch of vectors, A. Okay, so you look at all possible, okay, D tuples whose determinant mod P is non-zero, and then you just sum them up, okay, for all possible D tuples, okay? And this is this set. Now, with this set of vectors, we define now an ideal, a monomial ideal, which is generated by the monomials corresponding to these vectors. MP. Okay, this is what we call or what is called the logarithmic Jacobian ideal. Okay? Now, why am I writing all this? Because there is a theorem, okay, that precisely turns the problem of Nash, the original problem of Nash blowups into a combinatorial problem, and it is the following. So if you start with this A, okay, and then take the Nash blowup, then this is the same as taking the blowup of the logarithmic Jacobian ideal of the variety. Okay, so you turn the original construction, the original Nash blowup, into another blowup. Now, what is interesting here, what is good here, is that this ideal is monomial, okay? It is a monomial ideal. And in the toric world, we have combinatorial tools for describing the blowup of a monomial ideal, okay? So this is about Newton polyhedron, convex halls, semigroups, etc. Okay, so the original problem becomes a convex geometry problem, okay? A discrete geometry problem, okay? So this is the relevance of this result, okay? Now, this one has a very long story, okay? This was originally proved by Gerardo González Springberg in 1977. So I'm sorry, I'm going to write only the initials, but there's a lot of people involved here, okay? So this was proved by Gerardo González Springberg in 1977, okay? And for him, the variety has to be normal, and he works in characteristic 0, okay? Then Pedro González and Bernard Tessier in 2012, they improved a little the result by removing the condition of normality, okay? Still characteristic 0, but now an arbitrary toric variety. And finally, in a joint work with Jack Jeffries and Luis Núñez Betancourt, we gave the positive characteristic version of this result, okay, without the condition of normality in general, okay? So at this point, we were able to, we have a complete description of the Nash blowup in all possible cases, with normality, without normality, in arbitrary characteristic, okay? So now, okay, so this is the thing, okay? So with all these ingredients, we have this proposition, turning this into this. So now we study this one, okay? And so I told you, the problem is free of characteristic, okay? How do we prove it? Okay, so I'll give you the key step, okay? Key step, okay? Now, so consider, or let A be the subset of vectors that we found some minutes ago. Let A be such that IA is A2. Okay, so this set of vectors, but in general. Okay, now the claim is for any D tuple, okay, gamma I1. Gamma ID, the following holds. The determinant, usual determinant, of gamma I1, gamma ID, has only 3 options, okay, for this set of vectors. This can be 0, 1, or minus 1. Okay? And which hypothesis? No, just take A, the set of vectors that defines the 2 generic determinantal ideal. Yeah, this set of vectors. Yeah, but in general. Okay, so for any D tuple of this, huge set of vectors, the determinant can only be 0, 1, and minus 1. Okay, this was the difficult part, the tricky part of the proof, to prove this. Okay, but So why is this important? Because now notice that, okay, because of that, so here we're computing the determinant, okay? So we're computing M0, okay? But then notice that mod P, it doesn't change anything because mod P, all these numbers continue to be the same, okay? So in other words, M0 and MP are the same, okay, for all P. And the combinatorial algorithm, okay, begins with this set, okay? So you have like a machine, okay, that begins with this set. But the starting point is the same in positive P, positive characteristic or characteristic 0. So the result is non-singular because of Evelyn-Gusein-Sade. Okay, so this is the proof of the theorem, okay, the main steps. Okay, is it clear? Okay. Okay, so now we make a pause, okay, and then we change the topic suddenly, okay, we completely changed the topic, and now we're going to talk about Milnor fibers over symmetric determinant varieties for some functions, and also to deduce the value of the Euler obstruction at that point, at the origin, sorry, for those varieties. Okay, so let me move up, change the topic, and let us move to Milnor fibers over those varieties. Okay, so now, so we want to study Milnor fibers for some specific families of functions. Okay, so let me put them here. Okay, so consider this function. Okay, so let us take a close look to this function. So first we have several terms. Okay, this is like a Van Briscorn kind of polynomial with coefficients, non-zero coefficients. Okay, with some powers. And then we also have this second term, okay, that what we ask for this second term is that it's a polynomial whose Newton polyhedron is already contained in the Newton polyhedron of the first part, okay? This is the family we want to study. Now, this may look like I don't know, why this particular family? What would be relevant about this family? So this is no random family, okay? So as a remark, it can be proved that any non-degenerate polynomial function with isolated singular point with respect to some stratification has this form, okay? So we're working with a very specific family of functions, okay? So now we are interested in finding formulas for the Euler characteristic. Yes. Yes, of course. Yes, yeah, this is true. I was hoping that nobody was going to notice, but yes. So the thing is, where is the, here. So, okay, I'm going to move this all the way. Okay, I was going to talk about this a little later, but maybe this is a good moment. Yeah. Okay. So in principle, the ambient space for this variety is as to n. This is contained in some Cn. I don't remember this number, but the little n, okay, corresponds to, so recall that we have this set B such that the zero locus of I, or such that IB is B2, right? Now, this one has cardinality, this number, but we know that the cone of B, okay, so this is the all real, positively real combinations of this set of vectors. This one has n rays, and little n rays, has n rays. Okay, so recall that in the toric world, we associate to each element of B a variable. Okay, we only consider the variables coming from rays in the cone generated by B. We can clearly identify them. Okay? So this is the number of this little n. Okay, thank you for the question. Yeah. Okay, so let me start with the Euler characteristic, okay? And then we deduce the Euler abstraction, which here I want to thank Helen for giving the definition. This is a difficult definition, very long definition. So she already nicely introduced this definition. So if you have questions, please ask Helen, okay? So thank you. Okay. Okay, so let me start with this one. And as before, I'll show you an example, okay, of what we did, a simple example, and then I'll just give you the general statement, okay? So the first one, the smallest case, non-trivial, smallest case is S22, okay? So this is, again, the zero locus of IB, okay? In this case, this is contained in C3. And here, B is 1, 0, 1, 1, and 1, 2. Okay, this is the set. This is a surface. Okay, a toric surface, normal toric surface. Okay, so as I was explaining here, let me consider the cone generated by these three vectors. So you have 1, 0, 1, 1, and 1, 2. Okay, 1, 0, 1, 1, 1, 2. Let me call this Z1, Z2, because this will be the other ray, and C3. Okay, this one we don't actually use it. I mean, not for the function. Okay, so F is alpha 1, zeta 1, D1, alpha 2, zeta 2, D2, plus whatever polynomial that do not interfere with the Newton polyhedron. Okay, so now let me draw the cone generated by B. Let me do it here. Okay, well, maybe I can erase this as well. Okay, so the cone is as follows. Okay, so you have 1, 0, 1, 2, another one here, but you don't need it for the cone. Okay. So this is the cone of B, yeah. Okay, so the whole thing. We are in R2 here. Okay, and then let me mark some points. Okay, let me mark, because C1 corresponds to this vector. Let me mark D1 times that vector. Okay, so right here you have like maybe here D1 times 1, 0. Okay, the same for the other. So this is 1, 2. Let me mark here D2 times 1, 2. Okay, now let me describe the faces of this cone. Okay, so right now I'm trying to explain how we computed the formula for the Euler characteristic in this particular case. Okay, so I'm giving the ingredients that we need. Okay, so faces of C, and then volumes. I'll explain what I mean by that in a moment. So as usual, we have the origin, which is a non-interesting face. We have this as a face. Then another face is the one generated by this ray. Okay, so this is R greater or equal than 0 times 1, 0. The same for the other. 1, 2. And the whole face, the whole cone. Okay, cone. Okay, so we have these 4 faces in this case. Now, I want to compute volumes, but this is not like usual Euclidean volumes. Okay, we want to compute normalized volumes with respect to the lattice the face generates. Okay, so what is this? Okay, this example is actually simple, easy to explain. Okay, so well, this one not interesting. Okay, so this one. Okay, so this is the ray. Okay, it continues. Now I want to compute this normalized volume of this segment. Okay, and the lattice is generated by 1, 0. So in this case, it is actually the length of this segment. Okay, so the volume is D1. Okay, how many times you can fit 1, 0 in this segment? Okay, this is the volume with respect to the lattice. Okay, in this case, it is the length. Okay, now, but in the other case, it's not. Okay, so it's the same thing. Okay, I look at this ray, and I want to see how many of these vectors can you fit in this segment? Okay. Of course, D2, okay? But this is not the length, okay? So this is D2. Okay, so that was it for one-dimensional phases. Now, two-dimensional phases is a little more interesting because then, now you have to look at this region. Okay? And you also need to compute this normalized volume. In this case, you are looking at how many unit simplices can you fit in this region, okay? So in this case, you do the computation and it gives you 2 times D1, D2, okay? It's a simple example. Now, why am I interested in all these numbers? Because it turns out that in the toric case, okay, just like the Nash blew up, the original problem became a combinatorial problem. Well, here is the same. To compute the Euler characteristic, we use a general result by Matsui and Takeuchi, okay, that for non-degenerate polynomial functions, they give you a combinatorial formula, okay? And the formula, of course, involves volumes, okay? Very much in the sense that Alicia was talking about in her talk, okay? It's a computation of volumes, okay? You know, regions and etc. Okay? So I'm not going to explain all the elements in this formula. Okay, there are many things to explain here, but the thing is that this is a sum with changing signs of the volumes appearing here. Okay, so in this case, because of that Matsui and Takeuchi, so what you do is, so you take the sum of all one-dimensional phases, the phases and the corresponding volumes, D1 plus D2. All of them. Then you change the sign. And now you take the sum of all volumes in dimension 2. Here we only have 1. Okay? And then the formula would be, you change the sign, and then you take the volumes of all 3-dimensional phases, change the sign, and so on. Okay? So this is this formula in this very particular case. Okay? So what we did in general was to give, so what you need in order to apply this formula is to have a complete description of the corresponding cone, okay, in general. Okay, so in this case, well, it's very easy, but in general, you have arbitrary dimensions, you have some complicated phases, and you need explicit coordinates if you want to compute these volumes, okay? So this took some work, okay? This was the messy part of the work, but once we had that, okay, we were able to give the following formula, okay? So with the function I was considering before, and by computing bunches of volumes and looking at symmetries, etc., we arrived to the following formula, okay? Okay. Now, so this is for the Euler characteristic. Now, if you want to, now using the work of Bracelele and Seade that allows you to compute the Euler abstraction by reducing the problem to generic linear forms, we were able to deduce this corollary, okay? So the Euler abstraction for these varieties at the origin is 1 whenever n is odd and 0 whenever n is even, okay? Okay, this can be deduced using some formulas that Bracelele and Seade introduced or proved. Now, the relevance or the importance of these kind of computations, or one of the interest for doing these computations, there was a conjecture by Matsui and Takeuchi stating that the Euler abstraction should characterize regularity for toric varieties. Okay, in the general case, it was known to be false. I think Marcelo Saya gave counterexamples, but in the toric case, there was a hope, and this is of course a counterexample, right? Because the toric variety is singular and still has Euler abstraction 1. Okay, but I have to say that we didn't prove this, okay? This was known already, okay? Some other people with other methods, very different methods, already proved this. Actually, maybe this Euler abstraction maybe can be computed also with the methods that Helen introduced. Okay? So there are many ways for approaching this problem, okay? Okay, so I think this is it. Okay, so these are the results I wanted to share. And just to conclude, once again, I would like to mention again that I'm really thankful to Cidinha for opening the door, you know, for collaborations with the wonderful Singularity group of São Carlos, and I really hope that these collaborations will continue for a long time. Thank you.
So are there any questions or comments? Yeah. So,
Helge, yes. I'm sorry.
Okay, thank you. So my question is, in the first setup, when you consider determinantal varieties, if instead of a generic determinantal variety, you take a general determinantal variety, but for instance, the entries are monomials.
I see.
So is it possible to use your techniques, or?
I mean, first you need the corresponding determinantal ideal to be prime. I mean, binomial it will be if you take just monomials, but you need also to be needed to be prime in order to turn it into a toric problem.
Yeah.
If you have that condition, then of course the techniques could be used. Now, we didn't go that further because, I mean, we did this in February 2024. By January, no, by August we finished, something like that. And the counterexamples appeared in September. So I was, depressed. And so I stopped working for some time in Nashville. So yeah, we didn't continue. It was the project. It was the idea to continue working on determinantal varieties. So we didn't try. But you need these conditions, at least to be prime. And then it should be possible. Yeah.
okay. Other questions? Yeah.
So, again, regarding your first question, so I know you can't use the toric methods if you are considering the higher the generic geometric challenges for not the value of 2, but for t higher than 2. But do you have any idea whether or not the same result will be true there?
Yeah, thank you for that question. Actually, I would like to say something here that. So when I was asking Cidinha about this theorem by Evelyn Gussain-Sadie, she told me, okay, so the paper is this one, but forget it. They explain nothing. The proof is like this paragraph short. So you have to go to a paper by Helge where he gives all the details of that proof. So I read your proof, and of course the proof uses complex analysis. I mean, you take sequences, convergent sequences, but I remember, when I was reading it, that some steps are clearly free of characteristic. I'm sure. I remember very clearly that some steps, I was marking like, okay, this step is okay, this is okay. But there are others that you need to take exactly sequences and convergence, but maybe they can be replaced by some topological arguments, no? Not depending on the convergence. So I think it should be true. Yeah. Once again, I stop thinking of that, but I think it should be true. Yeah.
Thank you.
Any other questions or comments? Yes. Yep.
Hi. Yeah. Hi. Thank you for the talk. I was curious if you said that in the proof of the determinantal variety of minors, 2i2 minors, that the key step was that MP was equal to M0.
Yes.
I was curious that if for higher determinantal, like for order T minus, if the problem was that the determinants that you look for are multiples of P or something.
But you mean instead of working with M2 just to take any? No, the thing is that these are not, for T greater than 2, they are no longer binomials. So you're not in the context of binomial ideals. Okay. So that's the thing. Yeah.
Okay, thank you.
Yeah.
Any other questions, comments? Well, if not, let us thank Daniel again.
Thank you. Very good. Let's go for the barbecue. Azul.